Hello, this is on energetics today. So we'll be starting with enthalpy and bond energies. So first of all, what we have to know is that enthalpy or enthalpy change is the energy in a reaction. This usually as heat or some usually heat. So there's enthalpy change, which can be done at any pressure or temperature. However, they'll usually state that it will be a standard enthalpy change. Now, a standard enthalpy change means it's room temperature and pressure, so 298 degrees Kelvin or 25 degrees Celsius, and then the pressure will be 100 kilopascals, or that's 100,000 pascals. Now, if you remember back to year 1 and GCSE, there was exothermic and endothermic reactions. Now, an exothermic reaction gave heat out, think like an exoskeleton on the outside. Endothermic reactions take in heat, they need heat or energy. For both of these it's energy, not heat, but I've put heat. Heat, so endothermic need heat, they take it on in, so I think endoskeleton on the inside. So exothermic reactions, their delta H, should mention that delta H is basically the shorthand of writing enthalpy or enthalpy change even. So exothermic will be negative, endothermic will be positive. So in the example here, A plus B goes to C plus D. What we need to do is we need to break down the reactants into the elements. So A and B need to be broken down into the elements. Now, they'll usually give you the formation values for each of these, which will be negative. So, for example, negative 10 might be the energy needed to make A. So what we're going to have to do is we're going to have to times that by negative 1 to get the arrow going. Instead of from elements to reactants, we want that arrow going from reactants to elements. So we need to change the values, so times them by negative 1. So the red arrows here are would be positive, and the blue arrows are negative. So we want to go from A and B to C and D. So we need to go down from A and B into elements, so positive values, and up into C and D, which will be negative values. And remember to swap them. We times by negative 1. So remember, A and B break down, and then we reform to get C and D. Now, if we go back to that exo and endothermic reactions, we can draw the graphs. Now, you might have done this at GCSE. I certainly did all those years ago. So the exothermic graph. Now, we have our reactants, and we'll plot that point of energy on our graph. Then our products, our finishing point will be lower, as you can see from that graph just. Now, the difference between the two lines, so between the reactant line and product line, that will be our delta H, or our enthalpy change. So in exothermic, as you can see, products are lower than the reactants. That's because you lose energy, you give out the energy. Now in endothermic, we swap it around. The reactants start at the bottom, products finish at the top. Now this is because we need energy, we take energy in, we finish at a higher energy level. And remember, from that reactant baseline to the product baseline, that will be our delta H, or our enthalpy of formation. Now, at the top there in red, those lines, so from the highest point on that line, that curve, between endothermic and exothermic, not but on both graphs. That would be our activation energy, the energy required, that small bit of input to start it. So think of it like on your car, you turn the key and start the ignition then starts the engine. That's that first bit to get that fire going. You light a match and put it in the fire, that's that first little bit that you need. So then if we do an example here, so if we burn hydrogen in air, what will be our product? So we'll have hydrogen plus oxygen will go to water. That will be the reaction. So if we combust hydrogen in oxygen, we'll get water. Now, what we've got to do is we've got to establish our values. Now, the values will be given to you. They can be given you in two ways. So that's just showing you, that's where we're going to get our value. That's what our answer will be, that delta H. Now, where are we getting our values from? They'll either be given like that as showing the bond and then given the energy, or they'll be given the way I'm giving them now, which will be the H2 is negative 346. That just means the H2 bond. Now, O2 equals negative 498. That just means the O2 bond. And then as you can see at the end, it's HO. That now means the oxygen-hydrogen or hydrogen-oxygen bond is negative 460. So first stage will always be balance the equation. Always balance that equation. Second, draw your diagram out. So elements at the bottom, and as you can see, all these values are negative. So all our lines will be up and out. The formation of that bond is so negative 346 for hydrogen, negative 498 for oxygen. Now, as you can see, we've got our H2, which is HH bond. Now, we've also got our two hydrogens. So we're going to have to times that value by 2. And we want it going down to the elements. And because we want it going down to the elements, we times by negative 1. Times by 2, because we've got two hydrogens bonds. And then because we've got our two H bond H's, that's why you get that 2. Now, oxygen, we've only got the 1, so we don't need to worry about that. We've only got that one OO. But we do take negative 1 and times it by negative 1 because we do need to flip that arrow. Now, here for the water, 460 times 2, because in water you've got, it's H2O. There's two hydrogen-oxygen bonds. Now, we've times that by 2 again because we've got two waters, so there's 4 OH bonds. Now what we're going to do is we're going to do the sum of all these values, so sigma values, if you're a mathematician. So negative 1 times 2 times 436, negative 436 even, it will be 872, plus 498 minus 1840 will equal negative 470. That negative 470 will be our delta H, our formation energy. Next thing you need to know is colorimetry, or calorimetry, or calorimetry. Lots of ways to pronounce it. Never get it right. Doesn't matter. You just need to know what it is. So there's multiple equations for this. There's not just the one. And unlike physics and maths, you won't be given this equation. You have to learn them. So the equations, there's two equations. You have Q equals MC delta T, your moles equations, which you should know from GCSE and year 1. So your volume over 1,000 times concentration equals moles. So that'd be for decimeters. For centimeters, it would just be volume times concentration. And then you have your mass over mR, which equals moles. So rewriting that Q equals MC delta T as what they are. So you have energy. This will always be in joules. Mass in grams. Specific heat capacity. Now this is in joules per degrees to the -1, grams to the -1. So that's basically just joules per degree per gram times delta temperature, so change in temperature. Just showing you there that it's an inverse So that's from maths. So here we go. So centimetre cubed to decimeters. There you go. Mass is in grams. MR, you're going to have to find that and calculate that from the equation. So moles is mole in moles, and the moles will usually be less than 0. Only usually though. So our final equation will be energy in joules over moles. However, our answer is in kilojoules per mole. So we need to remember in between our first equation and second equation that we're going to have to times that by, divide that by 1,000 to get that into joules. So there's a required practical on this. Now, our required practical for it is on, you have to do a reaction for it. So if you're in an expensive or a school with a bit more money, you'll do a bomb colorimetry, which is basically the same as this. However, it uses more expensive stuff, and it's a 100% insulative box with a steel bomb in it, which is basically in here it's just going to be a cup or a can't remember the name. It'll come to me in a minute. So as will be a sample, which will be in our cup, which will be in our beaker of water. Now the water we're going to be constantly stirring to make sure our temperature is distributed evenly. There'll be a thermometer in there so we can measure the temperature change, and then that'll be in a polystyrene cup with a polystyrene lid. This is so we can reduce the heat given out to the environment, reduce the effects of it being lost. Now, usually you'll have a massive paragraph for the question. You'll only need your 4 things. You'll literally just need your mass of water, your mass of your product, your specific heat capacity, and your change in temperature. That's all you need from that question. Highlight it, keep it, move on. So I'm just writing them down here as if I've just taken them straight out of that question. Always write them down. So we've got 200 grams of water that changed in temperature by 8 degrees. Now, ethanol, 0.46 grams of it was combusted. Now, it says combusted. This means it gave out heat. It was burning. It gave out heat. Now, if it gave out heat, it's an exothermic reaction, so we know it will always be a negative delta H. So the specific heat capacity of water will always be given to you. It's 4.18. Don't have to memorise it. You can if you want. So our first step will be to find energy. So that's our mass, 200 times our specific heat capacity of water, which is 4.18, times by temperature. And this is going to equal 6,688 joules. Now, look, it's in kilojoules. We need it in kilojoules. So remembering to convert from joules to kilojoules, so 6,688 divided by 1,000. So we need to get it into kilojoules. So that's going to equal 6.688. I forgot the 8 off there. Apologies. Now, our second step is going to be to find the moles for our product. So remember, to find the moles, we're going to do our mass over MR equals moles, because we don't need volume here. If not, it would be volume times concentration, remembering that volume is in centimetres cubed. So 0.46 over 46, which equals 0.01 moles. Now, it's in kilojoules per mole. That's what we want, kilojoules per mole. It's per 1 mole. So 1 mole divided by 0.01 is going to equal our scale factor, which is 0.01. So we need to divide by 0.01 kilojoules value by 0.01 to get it in terms of 1. So 6.688 over 0.01 is going to equal 668.8. Now, the most figures that were given in the question were 3. So we're going to go down to 3 significant figures, which will be 6.69. And that will be an example of colorimetry equations. Now, they're not too hard. It's just you've got to remember your formulas and where you get your numbers from. Once you know that, though, it's quite easy. Now, our final stage here will be Hess's law. So Hess's law will be is basically finding the energy of an alternate route. For example, if we go back to our A plus B goes to C plus D, that will be delta H1. However, we could also say, if we go from A to B to E plus F to C plus D, these two stages will be equal to delta H2. Now, the formation energy, or delta H, or our enthalpy change, will always be the same, no matter how long the route is you take. So that's just shown there. Our alternate route is the same value. So the next bit is our thermochemical cycles. Sounds horrible, but trust me, they're not that bad. So, first thing we need to know is all our new delta H's. You need to know these again. They probably won't be given to you. Well, it depends, but you just need to know them. You need to know what they stand for. So delta HAT is your atomization energy. What it takes to go from condensed form of it to spread out, so your atoms, spread it out into the atoms. And you have your delta H, i.e. ionization energy. Energy to get rid of one of those electrons in the outer shell, or more, really depends. Then you have your delta H, EA. It's not the same as our activation energy. This now is electron affinity. Energy required to shove an electron on an outer shell. Next one is delta H, LEF, lattice enthalpy of formation. Energy required to shove those particles that are now spread out as atoms back into a rigid structure, back into that lattice. So from massive swirly mess back into our actual lattice. Now this is actually a reversible reaction technically, as we have our lattice enthalpy of formation, and we also have our lattice enthalpy of dissociation. Dissociation is just the opposite. So your enthalpy of formation will be a positive value. Your dissociations will all be negative values. So this, because it goes against the flow. So you need to know these. Please, please, please learn them. Right then, so the cycle. Now we're going to start by putting down our products. So in our example, we'll have aluminium oxide. So our products will be aluminium as a solid. And you must do state symbols. Please do state symbols, as we're going to be showing the change from a solid to a gas, or a gas to a gas. It doesn't seem that much, but honestly, you need to remember them. So aluminium add oxygen. I've already balanced it for you. Then below, on the line below, we're going to put aluminium oxide, our product, our reactants, then our product below. Now this arrow here represents our delta H formation, the direct route. Now we're going to do the delta H atomization of aluminium first. So here we go, 2Al, we've gone from a solid to a gas, plus 1.5 oxygen. Now I forgot my state symbol here, should be gas for both. Now we're doing the delta H atomization energy of oxygen. So we've gone from our 1.5 O2 to the atoms, which is 3. Now we're doing the ionisation energy of aluminium, so we need to strip 1 electron off. So aluminium becomes positive here. Now I put negative, I do change it. Plus our 3 oxygen. Now the next stage, because oxygen needs 2 electrons to fill its outer shell, aluminium needs to lose 3. So here we go. Now we have aluminium 2 plus 4 electrons plus 3 oxygen. So then we're going to do one more step of ionisation to get rid of that 3rd electron. Now it goes up in 2s because we've got 2 aluminiums. Now you could write it as 1Al minus plus 2Al plus E minus 1Al 2 plus 2E minus plus Al, and go that way, or you can group it like I have. Now the next step is we're going to go down, and we're going to 3 aluminium 3 plus 3E minus. Now we've lost 3 of those electrons as they've gone to the oxygen. They've made that oxygen negative already. Now we're going up because negative on negative repels. Negative on negative repel. So we need energy to put this in here. Just moving it over to get a bit more space. And then we're going to draw it back to our start line. So this is our delta H lattice enthalpy of formation. The 2 prior steps were our delta H electron affinity. Energy required to put those electrons there. Now in the exam you'll probably be given the values for each of the steps, and then to calculate the delta H formation, which is usually what they'll want, you have to do the sum of atomization energy, add the sum of ionization energy, add the sum of electron affinity, add lattice enthalpy formation, which will equal delta H. And to swap them around, we're going to do it like in maths, where we'll just make one of our values x. So, for example, if it was LEF, make LEF x. Then we have to move LEF over to the other side, which makes LEF negative. We have to move formation over, which would make it from a positive or negative value back to the other. And that is pretty much it for energetics. Thank you very much for joining me. Please watch other videos.